Hello. So this is our lecture on Introduction to Sequences. So we're going to be studying something called sequences and series in chapter 11, and so we're starting with sequences. This is our tiptoeing towards something more complicated. So we're going to go ahead and get started. I'm going to share my document with you, and we'll work here. So let's start with some simple definitions. So this is 11.1, sequences. And so here's a simple definition of a sequence. A sequence let's do this, is a list of numbers in a definite order. Okay, so to be clear, for instance, something like 2, 4, 6, 8 is a sequence, and something like 4, 6, 8, 2 is a different sequence, right? It's the same set of numbers. If we were talking about sets, these would be the same sets, but with sequences, we have a definite order to them, so the order does matter. These are two different sequences. Okay. And typically in this course, we're going to be dealing with infinite sequences. All right, so I might write something like this to imply that the pattern that has hopefully been established goes on forever, right? So this sequence here, what I'm trying to say is the sequence of even numbers, right, in ascending order. We won't have to deal with this, but just to be clear, this definition is a little bit too restrictive. We don't have to have sequences of numbers. There are places in math where, for instance, you'll do sequences of functions, sequences of vectors, and really anything you can put in order. So it doesn't have to be numbers, okay? So let's do a little bit of notation with sequences. We will often want to represent a sequence, a general sequence, right? So I might write something like A1, A2, A3, A4, right? Just to without having a specific sequence in mind, I could be talking about some general sequence. This is the first term, this is the second term, this is the third term, and so on. So for instance, in the sequence we just talked about, this would be A1, this would be A2, this would be A3, A4, and on and on and on. We don't have to start at 1. We will have plenty of times where we might start a sequence. I'll call this one B, where we'd have B0, B1, B2, B3, and so on. You might even have situations where you start at some other number, like C5, C6, C7, and so on, right? Typically for us, it will be 0 and 1, though we will have occasion to use something like 2 or 3. And we'll try to be clear about which one we're using most of the time. It's often pretty obvious from context once we get used to these things. So sometimes we might write, instead of writing this all out, we might write, well, sometimes, first of all, we might write these things with brackets. We especially do this if we're sort of writing about a sequence within a sentence or within some other mathematical ideas and separate the sequence out. We might just write this as A sub n to represent a very, very general sequence. We're not saying where it starts or ends, just saying we have some sequence of numbers. Or we might write A sub n and give some limits, like n goes 1 to infinity, okay? So that's just notation, right? So all of these things just represent a list of numbers in a definite order, right? With that being the first, and on and on and on. I'm going to make a little side note here, something that we won't have to deal with. We will think of sequences as a list of numbers in a definite order. There's nothing wrong with that definition. To be clear, a sequence is really just a function is a function whose domain is, so I'll just write z plus, this is the positive, sorry, I want to write, let's write whose domain, oops, I misspelled domain, whose domain is 0, 1, 2, 3, or some subset of this. Right, so I'm saying it's a function whose inputs are going to be whole numbers starting at 0 or 1 and going up, or something else, so some subset, like the example up here where we started at 5 and above. And so, for example, let's consider the function, do this over here, f of x equals 2x, whose domain is, let's say, the natural numbers. This is 1, 2, 3, and on up. Right. So f of 1 would be 2, f of 2 would be 4, right? I'm just multiplying each of these by 2. F of 3 equals 6, and on and on and on, right? This is the sequence we started with over here, right? This is the value of the sequence when it's at 1. This is the value at 2. This is the value at 3 and 4. So there are contexts you might see where this is a good way to think about sequences. We don't have to worry too much about this, but I don't want to. It is a perfectly reasonable definition of sequences as well. Okay. All right. So that's our definition of a sequence. Let's do a few other things. So, like functions, we sometimes give a formula for the general term of a sequence. So let's consider the sequence a sub n equals 1 minus 1 over n for n, where n is 1, 2, 3, on and on and on. Okay. So I'm defining a sequence by this formula. So according to this formula, A1, I'm putting 1 in for n. Again, they really are functions. I don't think the book talks about this, but they really are functions. I'm putting in, we're just using a different notation for them. Instead of saying A of 1, we say A sub 1. And then with this formulation, I put in 1 here. I've got 1 minus 1 is 0. A2, I put in 2 here. I get 1 minus 1/2 or 1/2. A3, I get 1 minus 1/3 or 2/3, and on and on and on. So we end up with this sequence 0, 1/2, 2/3. If you continue this, you'll get 3/4, 4/5, and on and on and on. Okay, and so instead of having to write out all of these terms, I've just given a nice little formula that we can determine the rest of the terms from. Let's do another example of a sequence. I'll use a slightly different notation. Let's say B sub n. Let's do it this way. Let's say this is the sequence -1 to the n over n times n squared over n squared plus 1. And I'll say n goes from 0 to infinity. Okay, so this is probably new notation for most of us, but this is telling us the general form of our terms. And this tells us where to start. And in this case, we're going to go on forever. Of course, we're not going to write all those out. But let's write the first few terms out. Okay, I'm going to use b this time. So b naught, b0, I'm putting in 0 for n. -1 to the 0 is a 1, so I'm not going to worry about writing that. I've got 0 squared over 0 squared plus 1, 0 over 1. This whole thing is 0. B1, -1 to the 1 is -1, so I'm going to have a negative in front of whatever I get. Then I'm putting in 1 for n here. I get 1 squared, or 1 over 1 squared, 1 plus 1, so negative 1/2. Let's look at B3. B2. Negative 1 squared is positive 1, so I've got a positive again. I've got 2 squared is 4. 4 plus 1 is 5, so I get positive 4/5. Let's just do one more. B3, negative 1 cubed is negative 1. I get 9 over 10, so negative 9/10. Okay. So there's our first few terms. So our sequence looks like okay. Right. So we see this sequence, for instance, has this nice alternating property that it's going from negative to positive to negative to positive, and notice that happens because of this term here. This is going to be a useful thing for us that we should make note of. And then finally, let's do one more example of a sequence. Let's take let's use C this time, and I'll use a different index besides n. There's nothing special about n. It's often used, but I'm going to use k this time. Let's say C sub k, the general term is going to be 1 over k squared minus 1 for k equals 2, 3, 4, and on and on and on. Right? Notice in this case, I have to start at 2. If I started at 1, I end up with a 0 in the denominator, which of course we can't have. And so here I get my first term, C sub 2, I get 1 over 4 minus 1, or 1/3. C3 is 1 over 3 squared minus 1, 1/8. C4 will be 1/15, and on and on and on. So this sequence looks like 1/3, 1/8, 1/15, ... Okay, so there are a few examples of sequences. Let's do one more thing to end this video. Let's do what we just did, but in reverse. So here I started with a formula and ended with a sequence. Now I want to start with a sequence and end with a formula. I think this is not obviously, but maybe obviously, likely the hardest way to do things, right? We all know how to do functions. This is essentially a function. Put n equals 1, put n equals 2, n equals 3, and so on. Now we have to figure out what this formula is by looking at the sequence. So let's do this example. Let's take the sequence, let me write it this way. Find an expression for the general term for the sequence -2, -1, 4/9, -5/27, 6/81, and on and on and on. Okay. So the general term means I want to be able to write something like, right? So this is just me thinking ahead. In the end, I should be able to write something like a sub n equals, and then there's an expression over here, right? Something like C sub k equals this, or a sub n equals 1 minus 1 over n, whose formula combined with the domain, the values of n, will give me this sequence. Okay. So this is a tricky business sometimes, and there's a few tricks I want to point out. The biggest trick is to not think about too many things at once. If you've listened to me before, this is a thing I talk about often. Okay. So first thing I'm going to do when I look at this is notice that it's going from positive to negative, positive to negative, positive to negative. I'm going to ignore that for now. The sign of each term is very easy to deal with. If you remember, we did this sequence a little while ago, and we saw this -1 to the n accomplished this switching of signs. So we're going to see if we can, so we're going to ignore that and deal with just the values of these terms, and then we can put the sign on later. So now I'm looking at the terms. There's something strange going on, right? If I ignore the first two terms, I see that the numerator here is 4, excuse me, 4, then 5, then 6, which is a pretty obvious pattern. And I see that the denominator is going from 9 to 27 to 81, which is a less obvious but maybe noticeable pattern. It certainly seems easily relatable to 3, right? And if we think a little harder, this is 3 squared, 3 cubed, 3 to the 4th. These two don't seem to fit into this pattern, except maybe we can rewrite them. So remember what I just noticed about the numerator. It went from 4 to 5 to 6. Well, this one's at 2 in the numerator if I think about 1 being in the bottom. Then I get my 4/9. Let's write it this way. 3 squared, 3 cubed, 3 to the 4th. Right? Remember, I'm ignoring the negatives for now. I'm just looking at the values. Well, in order for this pattern to hold up, I obviously need a 3 here, right? 2, 3, 4, 5, 6. And this pattern, 3 to the 4th, 3 to the 3rd, 3 squared, this tells me there should be a 3 to the 1 here, which makes perfect sense. 3 to the 1 is a 3, and there's a 1 there. And so this is just a different way to write the same fraction. And I might also realize this is 3 to the 0 power. Okay? So now, this gives me an idea for how to write the form. So let's decide, for instance, that I'm going to write a sequence, and I'm going to decide that I'm going to go from n equals 1 to infinity. Okay. What do I want the numerator to be? Well, this number for the first term is 2. For the second term is 3. For the third term is 4. So in each case, it's going to be n plus 1. All right, when n equals 1, it's a 2. When n equals 2, it's a 3. When n equals 3, it's a 4, and so on. Okay. In the denominator, I want powers of 3. When n equals 1, I want the power to be 0. When n equals 2, I want the power to be 1. When n equals 3, I want the power to be 2, and so forth. So this becomes 1 less than n. All right. Let me be extra clear about this. This is my A1 term, A2 term, A3 term, A4 term, A5 term, right? When A is 1, this is 1 bigger, this power is 1 smaller. This is 1 bigger than 2, this is 1 smaller than 2. That's where I get those two pieces from. Okay. Now, let's deal with the negative. So we ignored the negative here, but each of these should have, or every other one of these should have a negative in front of it. Okay. So now, I'm going to have this -1 to a power. Last time we saw this, it was to the power of n. Let's see what happens if we do that. When n equals 1 in this term, -1 to the 1 is a -1. We would end up with a negative here that we don't want. When n equals 2, this would be squared and it would be positive, but we want it to be negative. So what we do is we shift the indexing. So this is -1 to the n-1 power times that expression we just did. Okay? And you can check for yourself, right? Let's just do one. A sub 1, putting in n is 1. I get 1 minus 1 is 0. -1 to the 0 power is 1. 1 plus 1 is 2. 3 to the 2 3 to the 1 minus 1 is 3 to the 0 or 1. I get 2 over 1 or 2. It's the first term, right? I'll let you check the others, but this is a good habit to get in when you make these expressions. Make sure it's actually working. And let me leave you with one other exercise for yourself. Write something. And what I want you to see is what I have just written down is the same sequence of numbers. Okay, so if you put in, I noticed there's a slight difference. I've written down a different expression here, but I've also indexed differently. And so what we see is that this indexing, the way we write sequences isn't unique. Depending on how we index it, we might end up with a slightly different form of the equation. Okay, well, that's it for this one. Thanks, everyone. And I'll post the next ones soon.